beneath the complexities of everyday life, the rules of our universe seem reassuringly simple. This solid bridge supports my weight. The water flowing underneath always goes downhill. And when I throw this stone, it always flies through the air following a predictable path. But as scientists peered deep into the tiny building blocks of matter, all such certainty vanished. They found the weird world of quantum mechanics. Deep down inside everything we see around us, we found a universe completely unlike our own. To paraphrase one of the founders of quantum mechanics, everything we call real is made up of things that cannot be themselves regarded as real. Around 100 years ago, some of the world's greatest scientists began a journey down the rabbit hole into the strange and the bizarre. They found that in the realm of the very small, things could be in two places at once. That their fates are dictated by chance. And that reality itself defies all common sense. And at stake, that everything we thought we knew about the world might turn out to be completely wrong. The story of our descent into scientific madness begins with a most unlikely object. Berlin, 1890. Germany is a new country, recently unified and hungry to industrialize. In this newly unified Germany, a number of new engineering companies were founded. They had spent millions buying the European patent for Edison's new invention, the light bulb. The light bulb was the epitome of modern technology, a great optimistic symbol of progress. Engineering companies quickly realized there were fortunes to be made building streetlights for the new German Empire. But what they didn't realize was that they would also unleash a scientific revolution. Strangely enough, this humble object is responsible for the birth of the most important theory in the whole of science, quantum mechanics, a theory that I've spent my life studying. And that's because back in 1900, the light bulb presented a rather strange problem. Engineers knew that if you heated the filament with electricity, it glowed. The physics that underpinned this, though, was completely unknown. But something as basic as the relationship between the temperature of the filament and the color of light it produces was still a complete mystery. A mystery they were obviously keen to solve. And with the help of the new German state, they saw how to steal a march on their competitors. In 1887, the German government invested millions in a new technical research institute here in Berlin, the Physikalisch-Technische Reichsanstalt, or PTR. Then, in 1900, they enlisted a bright, if somewhat straight-laced scientist to help work here. His name was Max Planck. Planck took on a deceptively simple problem: why the color of the light changes as the filament gets hotter. To get a sense of the puzzle facing Planck, I'm going to ride this bicycle with an old-fashioned lamp powered by an old-fashioned dynamo. Obviously, the faster I go, the brighter the light. The more I pedal, the more electricity the dynamo produces, the hotter the filament in the lamp, and the brighter the light. But the light the bulb makes isn't just getting brighter. it's changing color too. As I speed up, the color shifts from red to orange to yellow.
Right, now I'm going to really belt it.
Now the bulb's filament is getting even hotter, but although it certainly gets brighter, the color seems to stay the same, yellow-white. Why doesn't the light get any bluer? To investigate, Planck and his colleagues built this, a black body radiator. It's a special tube they could heat to a very precise temperature and a way to measure the color or frequency of the light it produced. Nowadays, over 100 years later, the PTR still do exactly this kind of measurement, just much more accurately.
The temperature inside here is 841 degrees centigrade. I can feel the heat coming off, and it's glowing with a lovely orangey red color.
It's about the same color as my bike light when I'm cycling slowly. But I want to see something hotter still.
The temperature inside here is about 2,000 degrees centigrade. And it's glowing with a much brighter, whiter colored light. To produce light of this intensity and color requires a power of about 40 kilowatts. Now, that's equivalent to about 400 Ms on a bike cycling very fast, or the combined output of the entire Tour de France.
Although the light is whiter, it's red-white. There's very little blue. Why is blue so much harder to make than red? And further up the spectrum, beyond blue, the so-called ultraviolet is hardly produced at all, even when we look at things as hot as the sun.
Even the sun, at a temperature of 5,500 degrees centigrade, produces mostly white visible light and makes remarkably little ultraviolet light given how hot it is. Why is this? Why is ultraviolet light so hard to make? This remarkable failure of common sense so perplexed scientists of the late 19th century that they gave it a very dramatic name. They called it the ultraviolet catastrophe.
Planck took a crucial first step to solving this. He found the precise mathematical link between the color of light, its frequency, and its energy. But he didn't understand the connection. However, it was another weird anomaly that would really put the cat amongst the pigeons.
In the late 19th century, scientists were studying the then newly discovered radio waves and how they were transmitted. And to do that, they were building experimental rigs very similar to this one. Basically, by spinning this disk, they could generate huge voltages that caused sparks to jump across the gap between the two metal spheres. But in doing so, they discovered something very unexpected to do with light. They found that by shining a powerful light source on the spheres, they could make the sparks jump across more easily. This suggested a mysterious and unexplained connection between light and electricity. To understand what was happening, scientists used this. It's called a gold leaf electroscope. It's basically a more sensitive version of the spark gap apparatus. Now, first of all, I have to charge it up. What I'm doing is adding an excess of electrons that are pushing the two gold leaves apart. Now, first I take red light and shine it on the metal surface, and nothing happens. Even if I increase the brightness of the light, still the gold leaves aren't affected.
Now I'll try this special blue light, rich in ultraviolet.
Immediately, the gold leaves collapse. light can clearly remove static electric charge from the leaves. It can somehow knock out the electrons I added to them. But why is ultraviolet light so much better at doing this than red light? This new puzzle became known as the photoelectric effect. The ultraviolet catastrophe and the photoelectric effect were big problems for physicists, because neither could be understood using the best science of the time. The science that said quite unequivocally that light was a wave.